Okay, folks, this is the last theorem that we were talking about at the end of the last period. R is commutative ring with identity, and S a multiplicatively closed set with zero. I want to assume zero is not in the set. Then there's a one-to-one correspondence between the prime ideals of R that miss S, so the intersection with S is empty, and the prime ideals of R are localized at S. Given by this correspondence, take a prime in R that misses S. You look at its localization, P localized at S, which is fractions where the numerator is in P and the denominator is in S. That forms an ideal, and prime ideal of P is prime. And this is the way the correspondence goes. You might happen, well, what happens if P is a prime that hits S? Then what happens is this blows up. This becomes the whole ring. So it's not a proper ideal anymore. Let's kind of at least give an idea of why this is true. So sketch. Note first, if I in R is an ideal, then IS, which again, let me emphasize this notation. This is alpha over S, or alpha is in I, S is in S, is an ideal of R localized S. This is fairly straightforward to see. Let's go through this. Suppose alpha over S and beta over S prime are in I localized S. So the numerators of these are in I, the denominators are in S. Then, and let's just throw in the whole shebang. And RS is in R localized at S. So now this is just an arbitrary element of R localized at S. R can be anything. I'll call this S double prime. And S double prime is again an S. Then if you look at alpha over S plus beta over S prime times R over S double prime, this is alpha over S plus R beta S prime S double prime. And I can combine the denominators in just the way that you expect. This is S prime, S double prime. This is alpha S prime, S double prime plus R beta S. Now notice that since alpha is in I, then this piece is in I. And since beta is in I, this piece is in I, because ideals suck everything in. And because S is multiplically closed, that's the appropriate place. So this shows actually that I localized at S as a subgroup. Well, actually shows it's an ideal because I also did the multiplication by this. So there we go. That's an ideal. So in this correspondence here, this P localized at S is indeed an ideal. And so we're going to observe now that P localized at S is prime if and only if P is prime. So this is prime in RS if and only if P and R is prime. Okay, well, to this end, suppose first P and R is prime. Suppose we have a prime ideal here. We want to show P localized at S is prime. So let A over S and B over S prime be in R localized at S. Suppose that their product is in P localized at S. What does this mean? This means that AB over SS prime is the form P over S double prime for some P and P. And again, all my notation is that all the S primes and so forth are in S. Okay, so what does this mean here? I'm going to take the most general definition of this localization. So there exists a T in S such that T times A, B, S double prime minus P, S, S prime is equal to 0. Right? So this means that if I multiply this out and take this over to the other side, I get A, B, S double prime T is equal to P, S, S prime T. Now notice this is taking place at the R level, so this is in R. And I have A, B, S double prime T is equal to P, S, S prime T. Now, because of this P here, this is in P, so that means this product is in P. And so what does that get us? Well, P is a prime ideal. And so since P is prime, we have that AB, whatever it was, AB S double prime T is in P. This implies that A, B, S double prime T is in P. Because when a prime ideal picks up a product of things, it has to pick up one of the factors. Well, these two are not in P. Because remember, we're assuming that P misses that multiplicative set S. These animals live in S, so they can't be in P. So this means either A or B is in P, and therefore A over S or B over S prime is in P localized S. So P localized S is prime. So what we've shown is P is prime, and P localized S has to be. Let's do it the other way. Suppose I want to show that P is prime. And suppose that A, B, and R are such that A, B is in P. Now, notice here, I could do this rather conveniently. Notice that since AB is in P, then right? So what does this mean? This means that AB, because AB is actually an element of P, so this quotient here is in PS, right? Now, PS is prime, and so A over S or B over S is in PS. Right? So without loss of generality, let's say that A over S is in PS. What does this mean? Well, I'll be super careful about this. This means that there exists a P in P and an S prime in S such that A over S is P over S prime. Right? And again, I'm going to go back to the primitive notion of localization. What does it mean for these two fractions to be the same? There exists t, again in S, such that p times as prime minus ps is equal to 0, jumps across multiples. And I've got a similar situation to what I had last time. I have as prime t equals pst, which is in p. Therefore, AST is in P, so A or S prime or T is in P. But S prime T is not in P, because again, the set S misses prime P. Therefore, A is in P, so P is prime. Because we've shown that if A times B is in P, then in this case, A is in P. Okay. Now, what I want to do next is I want to show that the correspondence works. Notice that what this shows is this takes an ideal to an ideal, and if that ideal is prime, it goes to a prime ideal. So I've got that taken care of. Ideal goes to ideal, and if you have the prime option, then what you get is option. Now, what I want to do is to show that the correspondence is indeed one-to-one. It's a bijective correspondence. Is I need to show that any prime ideal is of this form. Any prime ideal, that's this form. So let's I'm going to call it Q maybe. Let Q in RS be a prime ideal. And my goal here is I need to show that Q is equal to PS for some prime P in R. Right? And this is what I need for the correspondence. Now, how am I going to do this? Well, Q is some ideal that is contained in here. So I am going to let P to be the set of, let's say, X and R, such that X over S is in Q. Basically, what I'm trying to do here is I start with this random prime ideal Q here, the Q that lives in RS. And what I'm doing here is I'm collecting all of its possible numerators, because I don't know much, but I know that Q lives in R localized at S. And so everything in Q is some fraction with a numerator in R and a denominator in S. I'm going to collect all the numerators, all the possible numerators here. I claim that P is an ideal. Of R. It's certainly a subset of R by definition. It's certainly not empty because, for example, 0 was in here, because 0 over S, the 0 element, has to be in this prime ideal. So let's let X, Y be in PS, or I'm sorry, in Q. Or no, I'm sorry, in P, right, in here, and R and R. Let's note here that S, Y over S prime are elements of Q. Right? Because that's by definition where I get X and Y from. Right? So now I want to show that this is in fact an ideal. So I want to show x plus ry is equal. Okay, so notice that are in Q. Uh, uh, so now what we need to do is show that x plus y is right. So we want to show that x plus ry, as a matter of fact. So also notice probably the best way to do this is I can kind of adjust this a little bit. Note that S prime x over S, right? And I'm going to hit this with an S. Sy over S prime are also in Q, because here what I've really done is well, multiply by S prime, but you can think of that if the ring's got identity, you can think of this as S prime over 1. If it doesn't, you can think of this as S prime squared over S prime, which is the same, accomplishes the same thing. So what's the point here? Right. So point here is I can adjust these by anything in S I want. So the way I want to get x plus ry is in here is if you look at x over S plus ry over S prime, these are both elements in Q. Right. I want to get that x plus y is a numerator of a single. I want to get this as a numerator here. And so what I want to do here is this. I want to multiply this by S prime over S prime, and this is S over S. So there's no harm in doing that, right? Still in Q. And I'm going to adjust this further because when I put this together, right, I want to be able to pull out what I want. I am going to put, this is going to have, I need an extra S and I need an extra S prime. So I'm going to multiply this also by S prime and this by S. These are all elements still of Q, because what I've done is I've multiplied essentially by 1 and I've multiplied by something that just adjusts the numerator here, which I can think of this as S squared over S if you like. When I add these up, and I've got the same denominator, so I'm shortcutting here a little bit, but it's the same equivalence class. So this is S prime. So what do I get? We have is in not an R. But remember, this is a prime ideal, and so we can reduce once again to this right here. Right. Now, one final thing is, let me point out that if you do the correspondence, now the correspondence in the other direction, we start with Q. This corresponds by looking at this correspondence here, looking at all the possible numerators, you get back to your prime P. And that's why it's 1-to-1. If you go here, you get PS, and then you have your PS, you go back to P. That's an easy check. And vice versa, if you start here with a Q, which we know is of the form PS, you go to P, and then you do this, you get back where you started. So this localization, this correspondence is exactly what you would want it to be. Okay, so I'm going to talk briefly about polynomial and power series rings. We did some of this in the homework to kind of warm up the polynomial part. I will repeat some of that, but not go through things in great detail. I want to spend this time to contrast this with power series rings. So let me give you kind of some definitions here. Just to make things easy, because some strange things can happen. Polynomials are kind of a familiar concept, but I'm going to assume that we have created range 1. Polynomials are our old familiar friend that we've done since maybe even high school, at least for some computations. Definition. Let R be a commutative ring 1. I'm going to define the ring of polynomials bar to be over R to be Rx, which is the sum of RKXK. So they're just polynomials, they're things like x and x squared and x cubed and so forth, only their coefficients come from this ring, whatever this ring R is, commutative with identity. Addition is given by so it's a ring itself. So I'm going to tell you what the rules are about adding. You might criticize me here because I have these sums both to n. if I wanted to be really general, I would have made this n and this m maybe, but I can't assume that they're the same, because if this is sort of a bigger polynomial, if it goes to a higher degree, I could just assume that some of the bigger terms on this actually have zero coefficients. So this really is general, even though it may not look like it at first blush. So you just add things step by step, collecting the polynomials at the same, or adding at each degree like this. And the multiplication looks like this. When I multiply two polynomials, and here I will do different degrees. Let's say SK, XK. So the R's and S's are both in R. This is 0. So that goes to the nth degree, to the nth degree. This goes to the n plus 1th degree, n plus nth degree, where CK is given by the sum K of Ri SK minus I. Okay, so let's do a quick example. Well, let me see here. So here's a quick example. This is how you multiply things, like degree terms. Let's say A3x3, A2x squared plus A1x plus A0 times B3, well, let's see, B2 x squared plus B1x plus B0. So what that formula means is you just multiply it willy-nilly, just use the distributive property, and you group things of like degree. So x5, there's only one way to make this. A3, B2, x to the 5, plus x to the 4. Well, I can make that with a 3 and a 1 to get a 4th power, or a 2 and a 2. So it's A3, B1 plus A2, B2. Notice the subscripts always sum to the degree, like you see in the formula there. This should be the last appearance. This is the x cubed term. This will be the last appearance of this leading term. A3, B0 plus A2, B1 plus A1, B2. And that's as far as I can go, because the next term will be A0, but there's no B3 to help me out here. B3 is 0. Well, now it's too small. X cubed, I can't get an x squared term out of this. This is A2, B0 plus A1, B1 plus A0, B2. And I get A1, B0 plus A0, B1 x plus A0, B0. So notice that, again, the sums of the subscripts always add up to the exponent. I've tossed around the word degree, so let me be careful about it. Definition. If f of x is a n x n plus a1, a n minus 1 x n minus 1 plus a1x plus a0 with a n not 0, then the degree of f of x is n. And sometimes we write it this way: degree f of x is n. The degree of a constant term is 0 And the degree of the zero polynomial is undefined. You might say some books sometimes find this to be negative infinity. The degree of any non-zero constant is zero. The degree of zero is undefined. And there's reasons for that we'll see in a moment. Theorem. You did a lot of this work actually in your homework here. Theorem 10.13. Let R be a commutative ring with one. Number one, R is an integral domain. Then the degree of f of x, g of x is equal to the degree of f of x plus degree of g of x, provided neither one of them are zero. We're assuming they're not the zero polynomial. If R is an integral domain, and so is Rx. Well, in fact, I'll state it this way. R is a domain if and only if its polynomial ring is a domain. 3, the units of R are precisely the units of Rx. If I is an ideal, I'm going to expand on what's written in the notes actually. If I in R is an ideal, so are Ix, which is just basically polynomials, all of its coefficients come out of I. And also, so is this Ix. This is the smallest ideal of the polynomial ring that contains all of I and additionally contains X. So it contains a lot. Basically, this is the set of things that look like alpha plus X f of X, where alpha is in I. So what the elements of I comma X look like, there's only one restriction. The constant term is in I. That's it. You got complete freedom after that. So these are all polynomials whose constant term is in I. These are ideals. Right. Let me write it this way. Then are ideals of Rx. There. 5. Rx mod Ix is isomorphic to R mod I X. That's from your homework. Here's something we didn't do, that you might try to prove. Rx modulo I comma X is actually R mod I. No polynomial involved there for that one. 6, I is prime if and only if Ix is prime if and only if I comma x is prime. And let me give you a word of caution here. I is prime. This means as an ideal of R. This last two, they mean as an ideal of Rx, because those things aren't even subsets of R. Okay, so let me move on to like slightly different waters here. I want to compare and contrast this theorem with formal power series. What is a formal power series, you might wonder? Well, that is just like polynomials, except there may be no degree in the sense that we write these symbols down and it goes on forever. So let me give you the definition of this and expand on it. Definition 10.4. Again, let R be a commutative ring with identity. The ring of formal power series over R over R is defined to be this is the set of A n x n, where A n is in R. So it's polynomials potentially without limits. Addition is given by the same way. A n x n plus add the power series B n x n, and you get the power series A n plus B n x n. And multiplication is the same way too. If I multiply these animals, this is the formal power series Cn xn. And the rule for the C is the same. That is, Cn is the sum k equals 0 to n of a k b dn minus k. Now, formal power series, let me point out that every polynomial is a power series, right? Because yes, this potentially goes on forever, but most of the coefficients might be 0. In fact, 0 is a power series. It's just the one consisting of all entries of 0, all coefficients of 0. So any polynomial is a power series. The converse isn't true. There are many, many power series that are not polynomials. Okay? You all have encountered power series probably the last time you thought about it was Calc 2 or maybe differential equations. But in those classes, what they did is we took the power series and started trying to plug in crap for them, right? Like I can certainly plug in 0. Can I plug in 1? Does it converge or not? This kind of thing. We don't ask that question here. We treat these things like symbols and we just add them and multiply, just like that. They still have meaning. In fact, they have a lot of meaning even without stuff plugged into them. Now, let me do a little bit of a comparison and contrast between polynomials and power series. And one example is, I'm going to give you kind of a foundation here. Here's one of the most striking examples. And that is, look at this polynomial with coefficients in the integers, 1 plus x. This is not a unit. One over 1 plus x is not a polynomial. Actually, let me change this to minus. All my statements so far are true, but it's just a little easier for me to mess with. Same situation. 1 minus x is polynomial. 1 over 1 minus x is not a polynomial. This is not a unit. Not surprising. 1 over 1 minus x, not a polynomial. However, if we consider this as an element of the formal power series ring, this is a unit. And here's the reason. I'll find you the inverse. This times this is 1. Because how do we multiply power series? Well, 1 times 1, that gives me the constant term. What's the x term? It's x minus x, so that's gone. What's the quadratic term, the squared term? It's x squared minus x squared, gone. Cubic term, x cubed minus x cubed, gone, and so forth. So when I don't have to stop, I actually come up with the inverse of this. And you might have seen this before. You might have actually seen this in Calc 2, only probably not put in these terms, because that right there is the Maclaurin series expansion for the function 1 over 1 minus x, right? Now, in your calculus, it would have said something like 1 over 1 minus x is this power series, and then it will give you the caveat if the absolute value of x is less than 1. We don't care, right? This is just a symbol, and notice that this functions as the inverse of this. That's a difference, one of the differences between polynomials and power series. For polynomials, the units of the polynomials were precisely the units of the coefficient ring. So in Zx, the units in Z are plus or minus 1. Plus or minus 1 are the only invertible polynomials as well. However, for power series, the units are much bigger. So let me give you kind of the analog theorem for power series here to marvel at. So theorem 10.1.5. So let's let R be a commutative ring 1. Number 1, R is an integral domain. If and only if power series ring is an integral domain. So this part of the theorem is exactly the analog to what was true for polynomials, because we just replace polynomials with power series, we get the same thing. The units are different. As we pointed out here, we can see that units are different. What do the units of R power x look like? Well, they're much bigger. They're all power series, where U is a unit in R and f of x is any power series. So in other words, let me kind of reinterpret this for you. How can you tell if some power series is a unit if it starts with a unit? If its constant term is a unit, game over, man. It's a unit. And that's an if and only if. If its constant term is a unit, it's a unit. If it's not a unit, its constant term is not a unit, and vice versa, right? So in Zx, the constant term is 1, it's a unit. This one starts with 1, it's a unit, end of story. 2 minus x, 2 is not a unit, and the integers, not a unit. And I'll kind of demonstrate why that's true. I won't give a formal proof of it. This analog works well. If I in R is an ideal, then I power x, this is perhaps what you think it is. This is just all power series where all the coefficients are in I. And I comma x, this is the analog of polynomial. This is the set of alpha plus x f of x, where alpha is in I. So in other words, again, just like polynomials, this is all power series whose constant term lives in I. After that, no restrictions. All you need is a constant term living in I, are ideals of R power x. If I is an ideal, I in R is an ideal, then R power x mod I power x is isomorphic to Ri power x. So this is analogous to polynomials, as is this. R power x modulo I comma x is isomorphic to R mod I. What else do we have? Just like in the polynomial case, we have I in R is prime if and only if I power x in R power x is prime. If and only if I comma x in R power x is prime. So you get that same triumvirate there of the 3 ideals. And finally, and this is different than polynomials. This one also, like the units, is different. M in R is maximal if and only if M comma X in R power X is maximal. So here's what the difference is with the polynomial, because there is some similarity there, but there is a difference. What's true for polynomials is this. If M inside R is maximal, then this ideal inside the polynomial ring is maximal. But the converse is not true, in fact, pretty much ever. The striking thing is not that when you start with a maximal ideal, you get this thing to be a maximal ideal in the power series ring. The striking thing is every single maximal ideal of R power X is of this form. So what this means, for example, is that if R is a quasi-local ring, so it only has one maximal ideal, then the power series ring will also only have the corresponding ideal, and it will also be quasi-local. This is not true. So, for example, if R is a field, the maximal ideal is 0. So, if you have F power X, power series over a field, that thing has only one maximal ideal, and it's generated by X, 0 and X. On the other hand, a polynomial ring over a field always has infinitely many maximal ideals. So this is the other direction, actually, right. The fact that, well, actually, let me correct what I said. What I've said here is actually true for polynomials too. If you have a maximal ideal here, then this is maximal. And if this is maximal, then it must be maximal. But all, so let me add the statement. This is the point I'm trying to make. All maximal ideals of R power X are of form M comma X for some M in R maximum. And that's the difference that's the difference from polynomials in this regard. Okay.